So, Geology 4. I think they're out of order now, but so anyway, so this is earthquakes. All this is here is earthquake pictures. Maybe you've seen these. Maybe you haven't. 1906. You ever hear of this one? The great earthquake of 1906 burned San Francisco to the ground. So this should be, since you've already now looked at plate tectonics a little, some of this should make sense, right? For these locations. Yeah. Anybody have any tectonic questions we need to deal with? A lot on out west here because of the major plate boundary out there, right? The San Andreas Fault. So there's one in, this is an interesting one, large crack in the ground. So one thing, if you ever watch any earthquake movies, one thing you always see is the ground cracks open and people are falling in and disappearing and there's fire coming up out of the ground and stuff. And that kind of stuff doesn't happen for real. This is pretty, sometimes the ground does crack significantly like that, but if you fell down in there, right, you wouldn't fall like to the center of the earth or anything ridiculous like that. There's been a few instances where a bay has drained out, or at one time there was an earthquake across the Mississippi River, and the Mississippi River flowed backwards for a while. But things like that are rare. But this is a significant crack in the ground from an earthquake. Alaska, that was a huge earthquake, made a massive tsunami. Larger than that one a few years ago. That was so bad, actually. Or in California. Japan has lots of them. So from your plate tectonics understanding now, you can notice where a lot of earthquakes are and what's the reason for them being California, Alaska, Japan. What are we talking about? You know what I'm referring to?
Are you talking about the one plate that's like currently like still moving? It's like shifting. It's not dormant.
They're all still moving, but why is there so much activity around Pacific plate?
Isn't it? I don't really know why, but isn't it called like the Ring of Fire?
Yeah, that's what I was. Yeah, whole ring of fire. So starting from South America all the way up North America, backwards from where South America, right, up to North America, Alaska, across over there to Asia, and everything down Philippines. So that's all the Pacific plate is moving this to the northwest, and there's a lot of subduction and sliding all along, all through there. So there's lots of volcanic activity, lots of earthquakes from plates sliding, bending, and snapping back into place, subduction, all kinds of fun things are happening there. So we don't really have to solo brainstorm. This is still from the asynchronous kind of thing. What do you know when you hear earthquakes? What do you think of? What do you know about anything? Somebody say anything.
Tsunamis.
The world shakes.
World shakes, creates tsunamis. Oh,
I think
tsunamis and
about
earthquakes.
the plates of the earth, like they shift and they like I don't know if they go like forward and backward or if they go up and down actually. But I know
Both.
they move. Oh, both. Okay.
Yep. It
I
depends.
think about the Go ahead.
I was just saying it depends on the motion and the type of plates. Go ahead.
I
Then.
think about like buildings like cracking and like breaking and stuff like that.
Good. And that there's that we're going to actually talk about why it's hard to build buildings that'll withstand that. That's good. What about, so that's sort of like preparedness, right? There was just, there's actually a lot of earthquakes in our area. Did you know that? I don't know if I mentioned that in a video at all that you've already watched, have I? In our
I
area.
remember one summer. Like I remember one of our picture frames like fell off the wall.
Yeah. Yeah, there's so in the
You
last
did mention it.
in the last like 8 years or whatever, there's probably been 3 or 4 in the area, right? And they're like, 4 point something, so you may or may not notice them. But there's a significant fault line that travels from down in the Tennessee area all the way up through where we are, pretty close to the Appalachian Mountains, all the way up into maybe, through New York, maybe up to the New England states. It records like 60 earthquakes every single day. And they're all minor ones, 2s and 3s that you wouldn't feel, you only detect with seismology equipment. But the point is that it's still an active fault line shifting. So someday, there'll be a big earthquake probably on the East Coast. The downside there, well, obvious downside, but in addition to that, we can just say the West Coast are ready for it, right? They build everything to earthquake code and they do earthquake drills and stuff, and we don't do any of that. So if there is ever a significant earthquake on the East Coast, we won't really be ready for it. And you know how people freaked out when we had those ones that you felt there that were like 4.2 and 4.4. And so you can imagine what'll happen then.
I have a question. It might be kind of off topic.
Is it earthquake related at all?
Maybe, I don't know. I was just thinking, you were talking about how earthquakes, when like the earth splits, how you don't like fall down like deep into the earth.
Mhm.
And it just got me thinking about sinkholes.
Hmm.
And I was wondering if that has any relation to like plate tectonics or if it's totally unrelated.
Sinkholes are generally in areas called karst topography, where the bedrock is made out of limestone, which is like chalk. So if we took a piece of chalk and put it into vinegar or anything acidic, it'll just dissolve, right? We'll have actually a chemical reaction, and it'll dissolve away the chalk, and it'll be something else. So places like Florida, even Pennsylvania, West Virginia has all those caves underground, right? And that's sort of what's happening there is water's running through and now more acidic rainwater, and it's dissolving the bedrock. And over time, you get a cave underground, and eventually if it thins out enough on top, then it'll collapse in. And it's oftentimes in a nice, neat little circle like that. But you ever go to any like Luray Caverns or Pennsylvania? I know there's a couple. There's like Indian Echo Caverns.
Those are really cool. I've
Yeah.
been in.
So if you go in those, think about it, you're underground, right? So that means they're huge, massive caverns underground. So if you're up there walking on them, you may be walking on very thin earth left over above that, right? So those are the natural sinkholes. And remember, a few years ago, there was some on the property of Disney World in Florida, and somebody's house, fell into one, and they never got the guy out. You remember that crazy story where they could hear him yelling, and they never? I don't think.
No,
they
that's
ever,
terrible.
I don't
That
think they
is
ever found him.
terrifying. I've
Why
never.
couldn't they get him out?
Sunk down into the ground. I mean, once you start getting deep underground, like there's a lot of pressure of things pushing in. I mean, maybe they dug him out. The last time I was
So
here,
he was like, was he crushed to death?
probably suffocated or something.
I actually just over the summer heard this story about a little boy. Well, he wasn't little; he was like about preteen, and he was swimming he was playing in the water like on the on the shoreline of the ocean, and all of a sudden he just like went under, and they were but he went into a sinkhole, and they were able to pull him back out, and he survived because he was like in like an air bubble.
Oh, really?
But any longer, and he probably wouldn't have been.
That's wild.
And then my sister was super freaked out at the beach with her kids.
I haven't heard many of those. So, I mean, they're rare. And the odds that you'd be over one when it opened are pretty slim. So I wouldn't go about life worrying about sinkholes all that much. But then there's some in the cities where like a water main breaks and it's just gushing water underneath the street and nobody realizes it for a while. It just washes away all the ground, and then the street will cave in. That's happened a few times in Baltimore. There's actually pretty crazy pictures of cars, right? right, have driven into the sinkhole, and, or sometimes like on the edge of roads, and that's not necessarily a sinkhole, but it's similar. It washes away the underneath the road, and then the road kind of collapses.
I think that's what happened near where my parents live, because I remember they had to shut off a bunch of roads because a hole just like opened up and a car like got stuck in it. So
Recently?
I think within the past like maybe 2-3 years or something like that.
Yeah. So that's water flowing, and I guess it's definitely geology related because depending on the type of rock, will wear away, dissolve away more than others, so it doesn't happen everywhere. All right, so earthquake. What do you know about earthquake predictions? Anybody? You know that's a huge goal, right? To be able to predict earthquakes would be great, right? Um, on their abilities to do that.
I thought, are you talking about like predicting like when an earthquake is going to happen, or like where it's going to happen, or like where it did happen?
Future predictions of likely when, right? Because they kind of know, like, there's a chance anywhere along the San Andreas, right, fault, for instance. But yeah, they're always trying to predict the big one so they can be prepared for it. But really, no luck. There's really currently no way to predict them long term. There's something that can happen, which we'll talk about here in a second, and then you know when the big part of it's going to happen. But all right, so let's talk about a few things here then. So if you want, I'll put this as soon as we're done. This whole slide will go into the onto the OneNote. So you don't need to copy down every single word here. So vibration of Earth produced by rapid release of energy. So that's the key. It's an energy wave traveling, not unlike a ocean wave, right? I don't know if we ever brought that up, did we? I feel like we have. But if you're standing at the ocean, watching the water come at you, it's really not water moving. It's just energy traveling through the water, right? Because all that water, all those waves aren't coming onshore. That'd be a lot of water that'd be moving from the ocean. So the water's not really moving. It's just energy traveling through the water, right? In the form of a transverse wave. So that's the same thing. It's an energy wave, but now instead of traveling through water, it's traveling through the ground. And the ground will actually take on the shape of that wave. Two different types of waves we'll talk about here in a minute. And that's what does all the destruction. Often caused by slippage along a break along the Earth's crust, which we call, well, there's the focus. So that's where the earthquake happens, actually, underground. So, and there's the word we're looking for right there, a fault. So a crack in the ground is called a fault. So when you were looking at the plate tectonics thing, those are major plate boundaries, major fault lines around the world. There's a lot more. There's faults everywhere. So if you go out anywhere there's like a little hill or a mountain, there's a good chance there's a fault, right? But this whole chunk here of this block of ground has probably lifted up over the years. It may take millions and millions of years for it to happen, but it slides along a fault line. So a crack in the ground is actually called a joint. And then once it moves, it's called a fault. So the earthquake might happen right there. So it might slide along each other for a very long time, and rock actually will bend. And then once because of friction, right? Rocks don't slide too well on each other. So once the force of movement overcomes the friction, it'll snap back into place. And right there might jump, a few feet. And that's what releases the energy from the focus. And then the point directly above the focus at the surface is called the epicenter. When there is an earthquake and they say where it happened, they will always name the epicenter above the focus. So it could be real deep, or it could be a shallow focus earthquake, or it could be a deep focus earthquake. All we're really going to talk about is the epicenter. Okay, so fault, focus, epicenter.
Is epicenter is that like the where like the worst damage will be?
Most likely, yes. Yep. Ground zero, so to speak. Yeah. I was gonna say sometimes deep focus earthquakes can be very bad if you think about this energy wave. If it happened right there, right? Let's say that focus was really close to the surface. Those waves, earthquake waves, don't travel through the air, only through the ground. And so once they hit the surface, they dissipate in the air. So if it happened right there, it'd be bad there. And it might not spread that far because it's so close to the surface. If it's real deep, it's got a long area to travel. So it might be very widespread. There's an animation there. If you want to take some time later to watch, you can. We'll just watch a little bit of this wild little animation here. Talk about a few things. This is actually for a Japanese security system, warning system. It'll show, here's all these little detectors all over the place. It'll show, but we just want to watch the waves happen for a few reasons here. We're going to move to where the earthquake. So this is going to show the earthquake happening. Far away. So right here. So we've got fault. This is rid of that. So this plate here is subducting. Remember that term, right? Subducting. And so right along here, it's going to be dragging this other plate with it. And then eventually, so it's building up energy, building up, and then it's going to snap back into place and release. There's two types of earthquake waves. E wave is faster, which we'll talk about more, and the S wave, which is slower. Our hopes, the goal with this is that it'll detect the P wave, which is not as destructive. So this is a little seismogram right here. It's going to show, there's the wave from it. Not too bad, and everybody has a chance to escape before the bigger second wave comes through. The alarm is going off. That's fun. So this is good. We're going to be looking at a lot more of this. And so also in the gizmo, you're going to be looking at seismograms. So this is a steady seismogram where nothing's happening. And then here's the P wave, the primary wave, and then you want to evacuate before the larger S wave, the secondary wave, hits. So as far as predicting an earthquake, they have not yet been able to make any predictions as far as just the earthquake's going to happen tomorrow or anything like that. They nowhere near that. I don't know if they ever will. The best so far would be that you detect the P wave, get the heck out, and then the S wave comes through. Oh yeah, if you want to watch so just like the way the energy wave travels through the ocean and transforms the water into a wave, the exact same thing happens to the ground. There's some wild videos out there of ground rolling and heaving and moving, and it looks not like rock, but that's what'll happen. It's hard to build things that can withstand both waves. Anyway, so there's something called the elastic rebound hypothesis, which is what we've been talking about. So it's really that idea of, this is better, to on the either side of the fault sliding past each other, and rock will bend and deform under stress and have a big bend to it, and then eventually it'll snap back into place, and that snapback is the release of energy from that is the earthquake. And so what'll come up soon here in a minute is we'll talk about how they measure the earthquake. The old style was the Richter scale. The new one is the moment magnitude. And so we could think about it like this. We could, I put a little something on here, a little spit water, something. I was shooting it, right? It's easy to see. It's easy to understand that the farther back I bend this, right, and let it go, the farther I'm going to shoot that little spit wall, right? Because I put more energy into it. So the more this bends, the more the energy is released. So that's the moment magnitude measurement. The more bending, the more displacement after the earthquake, the larger the earthquake. So it's a literal measurement of the release of energy, where the Richter scale isn't really that. They don't really use the Richter scale that much anymore, regardless of what you may hear on the news. So we'll just watch a piece of this too. I don't know if you can hear him or not, but this is just going to be, oh, and there's the fault line. So going to show you how fences move, and then show some deformation along the fault. So I don't know if you can hear him or not. So this is a fault line, and for whatever reason, this is always moving this way, and this is always moving this way, or they could be moving the same direction, just one a lot faster than the other, which is the same as moving in opposite directions. So they'll end up with this in California along that San Andreas fault, and doesn't have to be just San Andreas fault. There's all kinds of faults that break off from that. These are everywhere. Fences or roads or streams that are offset from one side of the fault to the other because of that. And then they can, over the years, they just keep getting more and more offset, and you can see how much they've moved over the years. That's what he's talking about right there. So instead of, at some point then, the rock will not keep bending. It'll overcome the friction and snap into place, and then that's the earthquake happening, releasing energy as it snaps back into place. And then it's like that, and we got so that's basically the elastic rebound hypothesis. So as far as measuring earthquakes,
Did you say that like the snapping back into place, that's what the earthquake is?
when they snap back into place, right? So they bend and bend and bend over time, and then when there's just too much force that overcomes the friction that's keeping that from snapping, it'll snap back, not into place, into a new place, snap back into shape. And then that is the energy that comes out of that is the earthquake.
Okay, thank you.
Two things that they use to measure earthquakes: intensity versus magnitude. Magnitude is measuring the energy released. Intensity is measuring the strength of shaking at certain locations. So we're going to look at both. We're going to do magnitude. I'll just tell you, magnitude is the more valuable scientific measurement because it's an actual measurement. Intensity is often comes from people's observations of things. Tends to make it not so perfect for science, but it's still very helpful. So we'll come back to the moment magnitude. So we can look at these here. There we go. Here's our definitions of the two. Measurement. This is how bad shaking is in an earthquake. You might look around. You can actually, this is what we're going to talk about here in a second. You can, if you were in an earthquake, you can go onto the United States Geological Survey website, the USGS, and you can tell them, call or type in online what you noticed, and they'll plug that into a map, and they'll assign a number to it, and you'll be part of the observation. And so it's sort of based on people and how they, if they were really scared, it might be that. If they really liked it. So magnitude is our measurement of it. And there's like the Richter scale, and there's the moment magnitude. And then we have this intensity scale, which we're going to look at the modified Mercalli scale. So Richter scale, most of the times now when you hear and they report it on the news, and then they say there was a 7.5. I don't even know if they say it anymore, even if they put a unit on there, so to speak. They used to always say 7.5 on the Richter scale. I haven't really used the Richter scale in a long time. It's moment magnitude scale, especially for the larger earthquakes. So the reason why is if you're familiar with amplitude of a wave, right? There's a wave. Amplitude is how far it diverges vertically off of the wave, either above or below it. And so Richter scale is determined using height of the largest seismic wave. So if we were looking at that little heartbeat looking thing, that's the seismogram, which we'll be looking at a bunch of, the Richter scale just measures off the largest one. So we could have, it could be just real tiny and then one big one, and that's going to, on the Richter scale, measure as a very large earthquake, even though it was only one little jump, right? Or oppositely, it could be a whole string of them all at the same height, either high or low, and it's not really a very accurate measurement. Where the moment magnitude is right here, using seismic moment, measure of the work done by the quake. So that's what I was saying. It's the actual slippage along the fault, right? So if the fault line slips 2 feet, then it's an actual measurement of how much energy is released from the rocks when this snaps back into place and has moved 2 feet. So it's a better system. The moment magnitude is, especially for larger earthquakes. All right. So that's really for your own knowledge. You're not really going to have to use the moment magnitude on the big gizmos that you're going to do. So what we have is this little Mercalli intensity scale. Look at that. So in the OneNote, if you're able to, there's a in the handouts section, a couple of the most recent things, little listing in there of the that's Mercalli intensity map. Oh yeah, so it's a PDF. If you want to look at that, right? It looks like this. So that has the Mercalli intensity scale and a map of the 1994 Northridge earthquake in California. You all probably remember that, don't you? Anybody? When were you guys born?
1999.
2000. Yeah,
97.
2000.
Did
So
somebody
this-
just say 2002?
Did somebody say that?
No, I said 2000.
2000.
My goodness. I thought somebody said 2002. I mean, well, 18. I guess.
99.
It's still blowing my mind that people are saying 2000, honestly. Anyway, 1994 earthquake, it actually happened during the World Series, and they stopped the game and stuff like that. It was really bad. And, so that's what this little thing is we're going to look at was based on. So as you can see, either it goes from 1 through, this one actually goes through 12. The one in yours only goes 1 through 10, which is better. So 1 through 10, if you were to read through these, you can see 1 is not felt, right? Marginal long period effects, all the way up through. You can read through these. Masonry is destroyed. Some of this says like rails bent. Like there's some significant things like this: frames cracked, serious damage to reservoirs, underground pipes broken. Large landslides. It talks about somewhere in here if water, like water in a pool, is moving. stuff like that. If there's little volcanoes of sand shoot up out of the ground, that's a real high level earthquake. Okay, so it's all based on things that aren't really measured, right? Does this make sense? Like an intensity, it's sort of just, holy crap, look what's happening over there. And so you would call it in, and they would give it one of those numbers. Okay, so you have this little map. So what we would do if we were all together, we would look at this map. So we got all these zip codes, right? And you could see down here, and you color code all of these. And then this would be the real exciting part right here, where in the OneNote, earthquake narratives. Did you see that? Look at those right there. Right? There's a whole bunch of them. I'll put a few in here. And these are actual people's stories, their narratives from that earthquake. Right? And you find a zip code. And I'm a nurse at a local hospital. I was attending to Mr. Jones, right? And so you'd read through these and you get some clues as to at that zip code, what was the intensity, right? Based on, specific things that were happening.
Oh my gosh, Professor, I was living in Peru when the earthquake from 2007 happened, and it was like a level 7 or 8. It was really bad.
The
And
magnitude was 7 or 8. What when was that? What year?
2007.
So you felt that 7 or 8?
Oh yeah, I did.
What did you
It
see
was
happen? Let's pretend you're the one of these. So what are some things that you noticed?
Well, we even saw like cracks on the floor. Like the floor was cracking.
Wow.
It was really bad, but
Were
I
you-
don't remember much of it, but I
Yeah.
remember the floor cracking and like kind of like waves. Like I couldn't see where I was going. Like I couldn't really walk.
Oh, okay. Oh, that's
So
good. Well,
it was pretty bad, yeah.
I don't mean that was good. So we could look down through here, and it actually, right here, look at this. 7, difficult to stand. Damage to masonry. Were you in a house or an apartment, or
Yeah, I was in my house.
did it crack the foundation? Do you know? You would know that. That looking like damage to masonry. So that's good. So we have like an authentic story here. Anyway, that's interesting. That's very fascinating. I bet no one else has been in a earthquake of that magnitude, I would guess. Right? That's a rarity. Cool. So they would then, if your family called in, then they would take they would take down your statement, and they would determine what intensity level it was, right? And they would plug it into the zip codes. So we would actually do that, a little bit of that in class for a while, and color them in different, and we would see some things. Went to this then, so now numbered in there is the intensity levels. All right, so you can see there's a 9er right there, right where, and so it's telling you this is after the fact, and this is where the earthquake epicenter was right there. And if we color code it, it's even better. So that we can see from this, even though it's sort of unscientific, right? But we still get a good idea of the intensity, of the earthquake, right? Very strong here. And then it weakens as it goes away, which makes sense, right? That's where it initiated. And then as you get farther, it gets weaker. And then we've got some weird hot spots. So there's all kinds of things that can go on depending on what country you're in and how things are built. A lot of lesser developed countries, when they have earthquakes, the damage is really bad. It may not be necessarily because of such a bad earthquake. It could be because of just the buildings aren't built as well, right? And so we could see the same thing here. Maybe parts weren't the same, or people had a more dramatic observation. Either way, but so that's an intensity map. How do you love that? Kind of interesting, right? You could be part of the, if you're ever in an earthquake, call it in. You could be part of the intensity map. Okay, so that's intensity. What we want to talk about is these waves. Okay, so types of waves. So these are just general waves. A transverse wave and a longitudinal wave. Let's make sure we understand the difference between the two of them. You've probably learned about these at some point in your life, I would guess. Right? So the red arrow shows the direction that the energy is moving, in both cases, left to right. And then the black line shows the way the medium moves as the wave travels through. So the medium could be air or water, or ground, anything, okay? We could use an example of transverse wave could be your jump rope, right? If I was holding one end of a jump rope and I flung it like that, it would make that kind of a wave, and we could watch energy travel down the jump rope. And as it goes down the jump rope moves up and down perpendicular to it. That's an ocean wave. So we were talking earlier, if you've ever been in the ocean before and you're out there a ways, as the wave goes by, all it does is move, it lifts you up and puts you back down, right? Because that's the water's not moving to getting close to the shore when the wave bottoms out. If you're out there far enough, it's just energy moving through the water in the form of a transverse wave, and it lifts you up, back down, lifts you up, puts you back down, right? So examples there are good. Would be a jump rope, ocean wave. Longitudinal wave now, the medium oscillates back and forth in the same direction that the energy is traveling. Slinky is a good one. If we stretched out a slinky and you pulled back a couple slinks on it and let it go, you can watch the energy, you can watch the wave go through the slinky back and forth in the same direction. It travels much faster. Longitudinal waves are generally faster because moving in the same direction, right? If you think about it, anybody a runner, long distance runner? Nobody? If you were out running, I don't know if you ever watch people run. When they're out running, they do a lot of crazy things. Like if you're running long distance, the one thing you want to do is save your energy, right? There's people that run crazy and like swing their arms across like this. You ever see that? Right? It's a total waste of energy because you're just kind of throwing energy over there in that direction. If you're running like this, everything's moving in the same direction. It's much more efficient. You're not wasting anything. So that's sort of the longitudinal wave. Everything's moving in the same direction, right? It's just maybe backing up a little bit. Energy is forced that direction. Same, right? Sound wave is a perfect example. Sound waves compress and release the air. That's how it's getting at least to the microphone, right? And then from your speaker to your ears. And the actual particles of air are compressed and then stretched out until they hit your eardrum. All right, so earthquake waves transmit both of these waves. And there's actually a third one that we don't even need to, but a surface wave. So when an earthquake happens, there's actually a longitudinal wave first, and then a transverse wave. And there's also surface rolling waves. So those all happen. The ground, in that case, the ground is the medium. So the ground will actually compress and stretch apart first, and then it'll roll just like an ocean wave. You can imagine trying to build things that will stand up on that. That's why things get destroyed. So it's a S wave, shear wave. So that's the transverse wave. You can call it the secondary wave if you want because it's slower. It comes second. Shear wave because it's kind of shearing things, right? Like if you were to cut something with a pair of shears, you kind of pull it in opposite directions. That's shearing. And the other is the P wave. You can see the ground will actually compress and stretch apart. Compress, stretch apart. So you can call it the primary wave if you want. So we've got the primary wave and the secondary wave, or the P wave and the S wave. Push pull. So this is the longitudinal wave. Faster one. It arrives first. So that's the weaker one that arrives first. Then hopefully the warning, and then everybody gets out of the building before the S wave arrives. And it all depends on how close you are to the earthquake. That's what we're going to talk about now. So what happened over the years, let's say you all had a seismograph, which detects earthquakes in your basement, you could pick up any earthquake around the world at any time. It might be very weak, ones and twos, but you would detect it. So earthquakes are happening around the world for years and years and years, and people would say, just had an earthquake. They'd transmit it, and they'd be like, yep, got it, P wave, S wave, P wave, S wave, got it. What was happening was that the people on the other side of the planet from every single earthquake were only getting the P wave, and the S wave was not getting to them. And the key is this here, I forgot to mention. So the P waves can travel through solids or liquids because of the way they move. S waves, because it's a shear wave, only travel through solids. Can't really, at least the earthquake wave doesn't travel through, shear its way through liquids. So for years they were like, why aren't we getting the S wave? So they had this S wave shadow zone on the other side of the planet. And eventually they figured out that it was because of the outer core being liquid. So you can see the P wave travels through there, and then the S wave kind of stop as it hits. I have another graph here of that. There's some really great graphs to show that. Anyway, that solved the mystery of the interior structure of the Earth. So now we know. We talked before. So the crust there is real super thin, and we've never even drilled through the crust. And you might ask, how in the world do people know about all of this? To a very high degree, it's not a guess. It's very well understood, and it's based primarily on the movement of seismic waves through the planet. They've measured them for years, and we now know, because of that, probably the exact size of the inner core and the outer core, what it's composed of, etc. Well, some other, divisions of layers through here. All right, that was a shadow zone, and now we understand that pretty well. So what we have is this. Here's a seismogram. If you were running your seismograph, and it was always basically, I have that in there. There you go. So it's basically this little pendulum hanging down. It's always drawing a line embedded into the bedrock. And then when the earthquake shakes it, it'll draw a line on there, right? It'll look like this. So here's nothing happening, and then earthquake. P wave arrives first because it's faster, and then sometime later, the larger S wave hits. All right? So the machine is the seismograph, the piece of paper or the recording, digital recording, whatever it is, it's called a seismogram that you'd actually look at. So here's a seismogram. P wave arrives, and then sometime later the S wave arrives. So we call this the SP interval, the lag time between the P wave and the S wave. Okay? Later, we're referring to this as delta T. I don't know if you remember from algebra or physics, we often use the Greek letter delta to mean change. Do you remember that? Ever come across that before? So delta generally in math and physics represents change. T is for time. So the change in time, the difference in time between the P wave and the S wave arriving is all that is. Okay. So what's important to think about is this. We know the speed of P waves. We know the speed of S waves. So we can use those to our advantage. And we can have graphs right here. Yeah, actually have a graph, and here's the distance of travel. So here's the P wave. And then here's the S wave. So some things we can notice are this. We can look at, say, if a P wave and an S wave travel for 10 minutes each, an S wave only goes 3,000 kilometers, while after 10 minutes, a P wave goes almost 7,000 kilometers. So we know P wave is much faster. Or we could look at it from this side. If we say 5,000 kilometers away from the earthquake, it took the P wave 8 minutes to get there, while it took the S wave 15 minutes to get there. Right, so the P wave is much faster. So the reason that the SP interval is so important is this. Ready? Here's an example. I'm racing Abby Marlowe. We're in a race, and we all know I run twice as fast as Abby does. Okay, so we're starting the race together at some point, and the rest of the class is at the finish line, right? And so we take off and we're running, and at the finish line, and remember, I'm twice as fast as her. If I come across the finish line, she's right behind me. What does that mean about where we started? If I'm twice as fast and she's right behind me.
You guys started
She started ahead of you.
closer to the epicenter.
Oh, well, look, you're already jumping ahead of the epicenter idea. You mean what about how long we must have been running for? If she finished right behind me.
She
A
was
short
running
amount
for a
of
shorter
time.
period of time.
A shorter period of time. Good. We weren't running very long. So the starting line wasn't very far away, right? If I'm running twice as fast as her, she kept up with and she finished right behind me, we didn't run very far, right? Whereas if you can imagine now, if I come across the finish line, she comes across an hour later, the starting line must have been pretty far away, right? That makes sense? So the same is true of the P and the S wave. So this is the difficult way to do it here, where we would measure this. We have an easier way. Here's the same. Does everybody kind of understand? So here's the distance between these two is the SP interval, right? That makes sense? There's the P wave, there's the S wave. We look here. There's the P wave. There's the arrival of the S wave. This is the SP interval. That's what this is here. And we can see this as we get farther away from the epicenter, the SP interval gets larger, right? There's me running. There's slow Abby running. And me just, right? So as we go farther and farther, I finish farther and farther ahead. So we can rewrite it like this. This is much easier to handle. So you can see here at 50 seconds, right? If the SP interval, if the difference between the P and the S wave is 50 seconds, then right here, we read straight down, the earthquake happened almost 500 kilometers away, 480, right? 480 kilometers away. That makes sense, how to use this graph? Anybody unsure?
How come there's only one line?
One line. This is just the combo of the two lines together, right? So here's the two lines, and we would be concerned with the distance between them, right? And so that's essentially what this line it represents is the difference between the two lines, okay?
That's also like the average, I guess.
Let me think. Would it be? I guess it would be probably close to the average. That would make sense.
How did you know to like go where to stop on the line, like where to go down? You said it was 500, but how come it wasn't like 600 or?
So if let's say the earthquake happens and you're at your seismograph station, right, and the P wave comes in, and then 40 seconds later the S wave comes through, and you have the delta T or the lag time interval, the SP interval is 40 seconds. You just start right here at 40 seconds, read straight across, and then when you hit the line that is the SP interval, then you go straight down from there.
Okay. So you were saying it was 50, so then that's how we knew.
It would be whatever, whatever it says on the seismogram,
Thank you.
right? And so if here we are, we'll pretend we're all at Towson. We've got a Towson seismograph station, and we have some, earthquake happens, and we record the P wave and we record the S wave, and it is, let's go exactly 51 seconds, right? The SP interval is 51 seconds at Towson. Then we would say, oh man, an earthquake happened 500 kilometers away from us, And that's all we know, right? And on the map, then you'd represent 500 kilometers in every direction with a circle, right? And that's all we would know at Towson. We'd be like, it was a big earthquake, and it happened 500 kilometers away from Towson, and that's it. It's somewhere on that circle. And so the only way we could actually find out exactly where the earthquake happens, we'd have to contact other seismograph stations. We'd call Baltimore, and we'd call Pittsburgh, and Philadelphia. Whoever's got a seismograph, and we'd be like, "Did you feel that earthquake? How far away was it from you?" And we would put all these circles on the map, and that's called triangulation. And the place where they all overlap is where the earthquake happened, right? Because Minneapolis is saying, "Yep, we felt it. It's somewhere on this circle." Detroit says, "Yep, we felt it. It's somewhere on this circle." Charleston says, "Yep, we felt it. It's somewhere on this circle." And the only place they all hit is right there. If we kept getting from other cities and it was the same earthquake, they should all intersect at that exact same spot. And triangulate the location. You know, there's the epicenter. And that's basically how we know, right? Because when the earthquake happens, it just happens and everybody feels it. It shakes everywhere, or it's detected everywhere. And then the only way to figure out exactly where is to go through that process that we just went through. So when you look at this, if you look at a map like this hopefully will be obvious and sound dumb for me to say, but it's not always the case. So these circles are not earthquake emanating out from those, right? The circle represents how far away from each station, each city, the earthquake happened. Okay? And we just draw those to locate the center, the epicenter. How do you feel about that? So there's just sort of a summary of what happens. The P and the S waves are detected, recorded on the seismogram. You just get the SP interval, or the delta T, which is the lag time between the P and the S wave, how far apart they are, right? And we know if they're real close together, the earthquake happened closer to you. The farther apart they get, the farther away the earthquake happened. So ideally, if there was a big earthquake, you would want a large SP interval. That means it's farther away from you, right? So then you use the SP interval, and it goes on that travel time graph, which is the graph with the 45-degree angle on it. And then you only know how far away it is from your location. It still could be in any direction from you. And then you have to triangulate. So you get at least 3 locations to determine the exact location of the epicenter. You could say at least 3 stations, at least 3 seismograph stations to determine the exact location of the epicenter. Okay. So basically, the 2 gizmos then are you locating earthquake epicenters. You're going to make that one little graph in the first one. And then in the second gizmo, you'll use your graph. You're going to make the travel time graph in the first gizmo. You'll use the travel time graph in the second gizmo to locate the epicenters of earthquakes.
So what is stronger? Is it the P or S wave?
S wave is stronger. P wave is faster. P wave arrives first because it's that push-pull, right? The longitudinal wave. And then the S wave is the stronger one, bigger one.
Okay. Thank you.
And then there's aftershocks, right? You guys always hear about aftershocks, but really, everybody's always like, it's just an aftershock. But an aftershock is just another earthquake. They're usually not as strong, but sometimes the aftershocks are stronger because it's not just an aftershock. It's literally another earthquake generally. So that's what you're going to do. Earthquakes 1 is the recording station. Earthquakes 2, determination of epicenter.